Okay, so we've looked at how we use a ticker timer to represent speeds, because we can count the gaps in the dots and we can measure the length of the section that we're looking at. So I want you to imagine that we've pulled this piece of tape through the ticker timer, and what I've done is I've sectioned it into pieces with 5 gaps each. So we've got section 1, 2, 3, 4 and 5, and there are 5 gaps between the dots in each of those sections. Now we know that the gap between 2 dots is 0.02 seconds, so if we multiply that by 5, we know that these sections each took 0.1 seconds to get through the ticker timer. Okay. If I measure the length of that section and call that L, so in each case it will be this length here, okay, so that's my L values for each section. I can find the speed that each section went through the ticker timer on by using my distance over time equation. Okay, so if for instance the section with 5 gaps is 1 centimetre long, my speed of my ticker tape at that point would be 1 over 0.1, would be 10 centimetres per second. If the length were 2 centimetres, let's say this one for example, it would be 2 over 0.1, giving me 20 centimetres per second. If it were 10, finally, it would be 10 over 0.1, and that would mean that the ticker tape went through at 100 centimetres per second. So what we can do is we can measure the length of a piece of ticker tape that has 5 gaps, and I can work out the speed of that tape. Okay. What I can then do is I can take the pieces, if I cut them, and I can arrange them in a bar graph, like so. Okay, so let me just get rid of my markings. Okay. Now I know that my x-axis can represent time. Okay, the reason I know this is because each section was cut to be 0.1 seconds. Okay, so each gap here between consecutive sets of dots must have taken 0.1 seconds. Okay, and we've just talked about how by looking at the length of the piece of tape, we can work out the speed of that piece of tape. So what we can actually do is we can plot a speed time graph with ticker tape. So I'm just going to remove this one and put a printed version up for you. And it will look something like this. Okay. So hopefully now you can see that we've stuck the pieces of tape, we've got the time going across on the x-axis, and we've now got the length. Now remember that what we can do is we can basically multiply the length value by 10 to get the speed at that point. Okay, because we've said a length of 1 would be 10 centimetres per second, a length of 2 would be 20 centimetres per second. So this one here must be 20 if we are using it as a speed axis rather than a length axis. And remember, a length of 10 centimetres is actually 100 centimetres per second. So I'm going to do my velocity in centimetres per second in purple as a different set of axes. So hopefully you can see I would have another axis that I could use. Okay, so a length value can be converted into a speed value because we've discussed that here. Okay, so now what we have is a speed time graph. Okay, so what we can then do, let me swap this because we've got a few more markings, is we can calculate the gradient of the graph. So remember that these black values here are lengths. So again, that would be 100, that would be 80, 60, 40, and 20. So that's hard to fit in. And in purple, that's the velocity in centimetres per second. So what I can do is I can take 2 points on my graph, just here, and I can calculate the gradient by looking at the change in y over the change in x. So actually, sorry, I've forgotten 1 0 just here, that should be 120. Okay, so I've got my first point I'm looking at is this one, and that's 0.1 and 20. And my second point that I'm looking at is here, and that's at 0.5, 100. Okay, I know that if I'm finding the gradient of a speed-time graph, I have acceleration. And hopefully you can also see that because as we go along, the gaps are getting bigger, we must have been speeding up, so we must have been accelerating, and the gradient is going to tell us the value of that acceleration.